So step by step, and if I were you, start with this, just to give you some hint. Start by finding what that is, the divergence. This is r hat here, the divergence of r over r squared, right? R over r squared. Okay, let's find what that is. That's from spherical coordinates, the divergence of a vector field is 1 over r squared, right? D over dr of r squared times r hat over r squared. Correct? And we can and there's no theta or phi dependence because it's only function of r squared. So the second two components are 0 of the divergence. Okay, this cancels that, right? And what do I get? Well, you get 1 over r squared d over dr times the derivative of 1. You agree? Oh, by the way, there's no r here because I am just taking the component. It's just a 1. And this is just 0. So you get a 0, right? Because that r squared cancelled. Right? Now, well, if you integrate this of VDA, right? Or that's just the V is just 1 over r squared, right? If the sphere this is a sphere radius r centered at the origin, so this would be 1 over r squared dot dA, and this is in the r direction, dotted with dA. So this is vector dA, so this will be 1 over r squared r, and dA in spherical coordinates will be r squared sine theta d theta d phi, right? Also in the r direction. And so when we dot these two vectors, we get 1, right? And this here is a double integral, so this becomes, so these two guys cancel out, and we get sine theta d theta from 0 to pi times d phi from 0 to 2 pi. And technically you just get this first guy gets you 2, the second guy gets you 2 pi, so you get 4 pi, right? So that brings us down to that the divergence of r over r squared is really nothing but 4 pi, right? Everywhere except at 0 because it blows up. So we would have to qualify this by a delta function at r. This is what I'm talking about. So you could replace this here, right, with this, with 4 pi delta function r. That's what it boils down to, because the solid angle integrates to 4 pi, right? Unless at r equals 0, it's going to be undefined because you're dividing by 0. So this kind of saves you. This says, okay, if you're at the origin where r equals 0, where this is undefined, this just becomes a 1 times 4 pi gets you 4 pi. So it rescues the function blowing up at the origin.
Okay. Wait. So I understand that with the gamma function, but then when it's not at the origin,
so it's 0. It's 0 everywhere. If you're not at the origin, it's 0 everywhere, except when you're at the origin. It integrates. It comes out to 4 pi.
But then wouldn't the function actually, like the actual function, wouldn't that have non-zero values when it's not at the origin?
Well, if you're not at the origin, the delta, you're not picking up the value of anything, right, other than 0, because this is telling you that the divergence is 0 everywhere except at the origin. And if you integrate it over the volume, which we did, you get 4 pi. These are the exact definitions of a delta function. So based on these two results, we say, okay, 0 everywhere else.
Oh, wait.
Except at the origin. At the origin, it's 4 pi. Therefore, my divergence will just be 4 pi times the delta function of r.
Okay.
Which would be 0 everywhere except at the origin.
Because we end up with
yeah, and now the problem from here on. Do you understand what I'm saying?
I think because we end up with the when we plug in that we get 1 over r squared times dr hat dr. But is there such thing as dr hat?
No.
No.
And now once you get this result, then it's easy. Plug it into the original integral here. So this becomes, so now the integral is just v, this thing, so 1 plus e to the minus r, and this whole thing turned out to be 4 pi delta cube r d tau, tau being the volume contained by this, right, the sphere. And now that's easy. Now this is by definition just the value of this function here evaluated at 0, r equals 0, right? Because if this guy here is f of r, the delta function only picks up
just at 1.
The 0.
So it would just be 1 plus 1 basically, so it would be 2.
So it's going to be 1 plus e to the 0, right? Because this is a magnitude of r. This is not like a vector r.
Either way, if it's 0, then it would be
so that, which would be 2,
right?
Oh, and then there's the 4 pi,
so it'll be 8 pi.
So it'll be 8 pi.
Okay, so then how come this becomes 0 everywhere that it's not, apart from the delta function? I mean, like, why does this turn into...
Look, we're looking at the divergence of r over r squared, right?
Yeah.
Okay, now this, by the divergence theorem, we've already done this. If you were to take 1 over r squared, right, d over dr, that's that, d over dr of r squared times 1 over r squared, this guy would cancel out and you get 0. That you understand?
Yeah.
You get 0. Okay, now if you were to integrate this, right,
Before evaluating it.
yeah, before evaluating it, and use the divergence theorem, the divergence theorem says that it's here. The divergence theorem says that the integral of the divergence on where is it? Let me just get it. Yeah, the divergence of f a d tau in general, okay, is equal to a closed integral of f whatever is inside your divergence, right? In this case, what's inside the divergence is r over r squared, so it'll be the integral of that dA. It changes a volume integral into an area surface integral, okay, closed surface integral.
Okay, so.
And so now if you apply this divergence theorem, right, because if you, so let's see, so let's evaluate. So this is 1 plus e to the minus r, right, over r squared, right, d tau okay, but the problem is this has an r in it too. That's where I think I'm hesitant to use that. You can't separate these two integrals. That's the problem.
Or maybe you can put it into.
No, look. Everything we did is correct. The answer is 8 pi. That's not what I'm questioning. What I'm questioning is how to show you that when you integrate this anywhere other than the origin, you get 0. I'm trying to prove it to you. But what we did here is completely fine, because here we just removed that divergence and we put in the 4 pi delta function and it worked out fine. We never removed anything outside the integral.
Right. Well, I'm saying, where did the 4 pi come from?
Oh, the 4 pi came when I integrated the where is it? When I integrated dA, this.
Okay. Yeah. Okay. All right. And how come you integrated dA? Like, why did you do that in the first place?
Yeah, because look, let me tell you why. if you're at the origin, forget all this math. Okay?
Yeah.
If you're at the origin, let's say you're here. Okay?
Right.
And let's say you have some arbitrary surface, whatever. We don't care.
Right.
Okay? And let's say the area, this is on d tau, right? And let's say the area you are considering is here. Correct?
Right.
Now R is big R. Well, this is a sphere. We should wait. Let's do this the question way. So this is a sphere. We know it's a sphere. Okay. Fair enough. If you're here, if this is a sphere, right?
Yeah.
You take a piece and you integrate it all the way around the sphere. What do you get?
You get the area.
Exactly.
Yeah.
That's how. It's 4 pi
Right.
r squared.
Oh.
Except you're dividing by r squared,
Divide by
which
r
goes
squared.
away, and you
Right,
get
so
4
get
pi.
Okay.
You understand?
Yeah. Yeah. Okay.
Okay, so the point being
wait,
is
I'm
this
saying
is the
how
right
come-
answer.
But how come, like, in the first place, how come you got from the volume to, why did you go from volume to area?
No, I didn't. I'm saying, forget the question. I'm trying to replace this
Yeah.
with what it is. And I showed you that this divergence aside, forgetting what the question is,
Yeah.
in every case, in general, it turned out to be, where is it? 4 pi this r.
Yeah, but I'm saying in the red, how come you did that?
Oh, okay. Then that's what I was trying to do here. But I didn't want to involve that 1 plus e
Yeah.
to the minus r. Okay, fair enough. Look, we are trying to find the divergence of r over r squared, right?
Yeah. Right.
Okay. So if you do the what we just did, you get 0.
Right.
Okay. Now, if r equals 0, this is no good.
Right.
So we have to think of a different way to do this if r equals 0. Now, what we do is we use the divergence theorem. The divergence theorem says if you were to take the gradient, the divergence of some vector function, let's just leave it simple, a, okay, and if you were to integrate this on d tau, the divergence theorem says you can turn this volume integral, this is supposedly 3 integrals, okay, you could turn it into a surface integral by removing the divergence, so saying that this is a double integral, just a without the divergence, so a being a vector, okay, dot dA. And I just showed you now, okay, let's do it. So in our case, a is r over r squared. Do you agree?
Yeah.
R over what was it?
Over.
R squared. R hat over r squared. Okay, but if we're on the surface small of the sphere, it's big R squared.
Right.
Okay?
Yeah.
And dA dotted with, right?
Yeah.
dA is in the direction of R, so we have here another R, right? Because it's perpendicular to the surface of the sphere, so it's in the same direction as R hat. Okay? The magnitude of dA. So basically, vector dA is scalar dA times R hat.
Okay.
You agree? Because on the surface, this is dA. It's in the same direction of R hat. r hat is in that direction.
Yeah, it's because it's always going to be in because it's a sphere.
Right. Now r hat dot r hat is 1.
Yeah.
Clear?
Yeah.
So you get double integral dA over r squared, right? Now this is a sphere. We just discussed that dA is 4 pi r squared.
Yeah.
Over r squared when you integrate it. 4 pi r squared over r squared. R squared cancels out and you get 4 pi.
Okay.
That's why.
Okay, and so the divergence theorem just basically
changes the volume integral.
Yeah. If it's symmetrical, then you can do that, right? But if it's not symmetrical, then that doesn't work.
No. You could do divergence theorem is very general. You could do that as long as it's a smooth curve with smooth continuous partial derivatives. Okay. So you pretty much can always do that in physics. Let's just put it that way.
Alright, so...
Okay, in this case.
So... Okay.
So then basically we proved that when it's not 0...
If you put the divergence theorem...
You get 4 pi.
Okay.
When it blows up. So back to the question. All I did then, I replaced this guy with what we just got. Yeah? 4 pi delta function r. And then from here on it's simple. It's just f0.
I'm assuming that the surface integral the surface integral would have a constant on it, but the divergence theorem the divergence theorem that the surface integral would have like a constant or something when you convert the volume integral to the surface integral. Is there like an extra constant that goes in there?
Yes, there is, but I completely ignored it because it doesn't really matter. Because I mean, in our case, it's 1 over r squared. I didn't write it out, but I left it 1 over r squared.
Yeah, I thought because there's that extra information that you need to account for.
Yeah, but basically this is the divergence theorem here.
Okay.
It turns d tau, volume integral, into surface integral.
Okay, alright, so... Okay. Alright. Yeah, the middle part is the...
Okay. So